to CompPoly. Okay, so I'll do a quick intro so that we don't lose too much time. So next talk is about CompPoly, that is computable polymers in Lean, and generally turning our specifications into executable specifications that we can run. So this talk by Derek from the EF, and obviously kind of joint work with, as with every other thing we're talking about today, many other contributors from Nethermind and ZK Security.
Yeah, great. Yeah, thanks. In fact, okay, so one thing to mention is that I've written my slides today in Lean, and so all the code you see, unless it's a screenshot from VS Code because it was too hard to put into the slides, they all type check. And so, yeah, like Alex mentioned, loads of collaborators. I've listed all the GitHub handles of direct contributors to CompPoly with this little screenshot, and then we also have our faithful AI contributors helping us all the time. But yeah, so all of this, lots of people in this room have contributed, and yeah, this is joint work with a lot of people. So, like Alex mentioned, we are the goal of CompPoly is to make our specifications in ArcLib all computable, and I guess by computable we mean executable. And so we want to be able to run ArcLib as a proof system in principle. And so. In order to do that, so yeah, our ArcLib is primarily right now a specification framework for snarks in Lean, but because Lean is both a proof language and an actual functional programming language, the difference between specs and programs can be a little bit blurred. And so we're asking the question, can ArcLib be an effort to build proof systems in Lean and snarks and things? So the computable core of all of that effort is CompPoly. CompPoly is a little bit of a misnomer. It started out as polynomials. We've added field specs, and there are conversations to add loads more algebraic things, like was mentioned in Julian's talk before. So yes, it's meant to be the computable engine. So maybe the first question is, why do we want computable specs at all? I think there are lots of answers to this. I guess in the early days of formal verification, I forget what decade, maybe the 70s, 80s, there was kind of this battle between do we double down on testing to secure our software, or do we try to formally prove things? One of the arguments that has been salient over the decades and is still used today is that if you're writing software, the very process of writing down a specification forces you to think very precisely about what you're building and will help you encounter edge cases. So even if your specification can't even really be connected to the code in any formal way, writing down a formal specification is just a good idea. We've made so much progress in the last few decades of being able to connect code to actual formal specifications that we are now in a position where we can build these huge specifications in Lean, and trying to specify something like a proof system in Lean turns out to be a large engineering project in itself, and specifications are code, and so we want to take it a step further and ensure that our specifications are correct. So the first thing to point out is that formal specifications are programs, just like the programs that we're trying to verify them against. And so they can have bugs, and therefore, if we can make them into programs that we can run, then they can be executed. And there's a long history of executable specs from a low level to a high level. Like TLA Plus is a good example of that, of you write a spec, and then you can actually run it in some runtime. And that will help you find more edge cases of your spec, which in turn helps you ensure that the program itself is correct. Second point to make here is that specs are very hard to write correctly. A formal specification is supposed to be a description of what you mean by correct when you refer to software. And software is very complicated and has loads of edge cases at all levels of abstraction. So specs themselves are hard, especially for new and emerging technologies like snarks. And so the field hasn't had time to really make concrete, stable, and distilled the specs that should be kind of universally used. There's new research coming out all the time, and like Alex mentioned before, there's the research on paper, there's the implementations in the wild, there's the lore surrounding everything, and then in our formal specs, we're trying to sort of figure out what the quote-unquote canonical thing should be. And so part of that, so they're just hard to get correctly. And then maybe taking a very short, more philosophical take on formal specification is that the line between specification and program isn't a program that gets compiled down to bytecode, just a specification that you've written in a language where you're specifying your bytecode. And so there are many levels of abstraction. We're already, I would argue we're already working in specifications if we're writing code, and in ArcLive we're trying to be a higher level. And I would say maybe the very best specification in this case is actually a formally verified reference implementation, which is ArcLib. So, okay, there's more to say there, but it's too much of a tangent. So we'll just go straight into CompPoly. So CompPoly started with polynomials, and I'll be talking mostly about polynomials in this talk. Polynomials themselves, of course, are essential in snarks and everything we're doing, to the arithmetization, to the IOPs, commitments, to Fry. And like I said, there's more than just polynomials here, but yeah, very, very important. But polynomials are also just universally applied all over the place. And so a library like CompPoly, and just like a computable, efficient, algebraic library for these primitives that are so important, has loads of applications all around, including computer algebra systems. So these first two examples I've written here are two ideas that are actually people in the wild implementing things who have been curious about CompPoly. So computer algebra systems got a message just the other day. Turing machines, that's an ongoing project. But then, numerical methods, coding theory more broadly. And I think CompPoly is interesting because MathLib already has a robust library of polynomials in Lean. They're, of course, non-computable, which is what we have been using in the past in ArcLib. But I think one genuine use case for CSLib is to implement well the non-computable definitions in MathLib and kind of have a mirror. And what we're hoping for with CompPoly is that this can be a good, maybe a good example of doing that kind of set a precedent for other efforts to make computable definitions, certain definitions in ArcLib. Sorry, in MathLib. The goals of CompPoly, the first goal, I guess, is to be a canonical reference of computable polynomials in Lean. We want this to be as widely used as possible and as robust and as efficient and as kind of nice and clean as possible. We want it to be flexible enough so that it can be used all through the Lean ecosystem for various things, and we also want it to be efficient. And that is something that we're working on right now. People in this room are actively working on making it efficient, and I'll talk about that a little bit later. And so in what remains of this talk, I will kind of give an overview of the structure of the library, the philosophy that we've taken in building it out, some of the roadmap and goals, and then this third point, I have some new results as of this week of formal verification with CompPoly that has just started. Right, so the core definitions for polynomials is we have univariate, we have bivariate, we have multivariate, and multilinear. Of course, the univariate and the bivariate are special cases of the multivariate and et cetera. But we've actually chosen different data types for each of these for various reasons. But we do have the relevant isomorphism theorems. So univariate polynomials are first defined, they're coefficient arrays. So in CompPoly, we have what we've called kind of the raw polynomial layer, where these coefficient arrays can have trailing zeros. And then we have this is canonical predicate, which just says the last coefficient in the array is non-zero. And then the canonical, we're mirroring the MATLAB definitions. So there's the polynomial definition in MATLAB, and we're just putting C in front of the relevant MATLAB definitions for computable canonical. So in this case, what we're calling canonical univariate polynomials are coefficient arrays modulo the is canonical predicate. And what I mean by that is they're just trimmed coefficient arrays. Bivariate is our nested nested univariate polynomial, so it's a polynomial of a polynomial. Multivariate is this is different. So I guess the univariate case, we have dense coefficient arrays. Multivariate case, the data type that is used is more optimized for for sparse polynomials. And so there's this extensible tree data type that's used to map the monomials to their coefficients, and this lawful definition is, so I guess I kind of put it the other way around. So there's, similar to the univariate case, in this case, there's an unlawful version which has zero coefficients, and then we quotient by the kind of trimming operation to get multivariate polynomials. And then there's also multilinear, which is a tree map from monomials to coefficients as well. Oh, sorry. Right. Which for multivariate. Let's see. I don't actually spend very much time. Julian.
I actually wrote this. So
Yeah, Julian wrote this. Yeah.
The first thing is a monomial, which is a mapping from fin n to a nat, which is basically for your monomial. It maps the fin n's basically are the names of the different variables, and it maps to the degree within the monomial, and so it maps each monomial to its coefficient. So the x-tree map maps a monomial to its coefficient amount, essentially. Right? So does that make sense? And then the third argument is just because the extensional tree map needs an order to be able to get the logarithmic performance in fetching different things, and so we just give canonical order of the reloads, essentially. So, answer your question? Yes.
Nice. Thank you, Julian. Right. Okay. So the general pattern that we've shown. So I've just shown you the basic definitions of what we mean by the polynomials. And the goal here is, because the goal here is to have a computable version of the non-computable definitions in MATLAB, we need our relevant ring isomorphisms. So what we do is we have our basic definitions. We implement a very basic API, just standard operations on like add, subtract, multiply, and I guess we'll see them in just a second. And then we have these functions that take your computable to the non-computable and back, and we have ring isomorphisms that we prove. So we have ring isomorphisms for all of these, and we have definitions for everything in the relevant theorems. So for example, in the univariate case, we have add, an add operation, which is exactly what you think it is. And then we have these theorems that show that addition, as long as you have a semi-ring, that if your polynomial coefficients are all in a semi-ring, then your addition is commutative and it's associative. And we go further, with the multiplication to prove all of the ring laws. The basic polynomial API includes getting the constant polynomial here, the variable getting just having a single variable, and the coefficient function, which gives you the coefficient at xi in x to the I in the univariate case. And then we have this function to and from. Oh, that's funny. Oh, you don't. Oh, good. You don't see that. Okay. There's a anyway. Right. So we have two poly. This was very hard to write in a way that would type check, and so I've just had lean output this very ugly version. But the point here is that we have a two poly function here. Right here, and we have a two impl, which takes you back to computable, and then we have the ring equivalence, which says C polynomial R is isomorphic to the polynomial ring. And part of that is that is to prove that we had to prove that addition over this this isomorphism, addition is as you would expect, same with subtraction, multiplication. Anyway, just basic ring isomorphism. Proofs. So I guess we have our minimal definitions, and we define as much as we need to get the ring isomorphism, and then the goal from here is to delegate all of the proof infrastructure to Mathlib, and basically none of it to CompPoly if possible. So proof strategy is if you encounter a computable polynomial in Lean, you hit it with the isomorphism, and then you have this beautiful plethora of theorems from Mathlib that you can use to your heart's content. So an example here is work that Julian here did for the Lagrange interpolation, and there's just part of this is defining a basis divisor, and then the relevant lemma shows that the basis divisor under the isomorphism is what. So this lemma proves that the computable basis divisor function is correct, and that is showing that it is the same under the two poly isomorphism as the one already defined in Mathlib. And so the really nice thing about this is that in this case the proof is very simple, but it's taking advantage of all of these kind of isomorphism theorems that have already been proved. So the idea is with CompPoly, proofs should really just follow from Mathlib. Right. So we have all the definitions as of maybe a month or two ago. All of those are nice and done, and we're currently in the middle of phase 2 of trying to push efficiency as much as possible in CompPoly. So we want these to actually run in a reasonably efficient kind of production mode. And so we have, like I said, many people in this room are already working on this. So for univariate, we have FFT, NTT, currently being, in fact, FFT was recently finished and it will be merged soon. Multilinear, we just started with folding, batch evaluation, efficient factorization of bivariate polynomials, fast field arithmetic, exponential optimization, efficient decoding, error correcting, all of this. So we're in the middle of this large push to make this a reasonably efficient library, and then we'll kind of fine-tune from there, which is very exciting. Which means that we're trying to push the limits of Lean as an actual functional programming language that could, in principle, run in production. And so we're very excited about that. And then, yeah, Alex has a lot to say about compilers and these like that to make it even more efficient, and maybe we'll just do everything in Lean. It's all very exciting. Right, so I have some slides. I'm running out of time, so these are code excerpts from some recent progress from people in this room to make these polynomials evaluate more efficiently. And then finally, I want to share that the goal of all of this, like I said, is to have really good specs in Lean, and that means that we should be formally verifying things in Lean. So we've been working hard, and by we, again, I mean people in this room, have been working very hard to get the extraction process from Rust into Lean, because most of the ZKVMs that we care about are all in Rust, and we want to verify them in Lean. And so we've been working very hard with people, experts in extracting this. And we recently were able, the tools are getting to a reasonable place, so we're able to extract some of the relevant crates in Plunky 3. So this last week, I extracted Koala Bear. And the process this looks like kind of in the wild on the ground is you have your crate, your Rust crate. You can extract the Rust, and it will extract into this proofs directory. And what it does is it gives you a Lean file. You build all the Lean infrastructure around it. and then you can import CompPoly, for example, and formally verify things. And so I've managed to get some. These are very basic proofs about Koala Bear that just essentially say that the relevant constants are what we wrote down in our specs, which is almost trivial to prove, but it is a starting point. And the goal is to expand on this and hopefully to bring all of the ArcLib specs into direct application to production code. And CompPoly is the vanguard of that, being the most basic, kind of computable, kind of most fundamental piece. And that's all I have for you today. So thank you.
Katie, do you want to switch over or do questions?